Well, warm welcome, everybody. Thank you for being here in a new location from within the void, of course. So it's exciting to record from here. Get yourself ready. Grab a notebook, pencil, or a pen. Whatever you choose to write with is fine. This is math. Beachside from the void. Math coming at you out of nowhere, hitting you like waves. How about that? And today what we're going to be doing is we're going to be going over some calculus prep focusing on algebra. So there are going to be about 4 or 5 main topics, big picture topics that I want to get into. That way when you get to calculus, you're not going to get slowed down by some of these obstacles. These hurdles that a lot of calculus students are troubled by should not really be that troubling. When I see them working, it's like watching somebody who's competing in a track and field competition in the hurdles run, right? And you see people tripping over hurdles that are not even as high as their knees. And I'm like, guys, you shouldn't be getting tripped up by these. So the purpose of these series here, the Calc Prep Algebra section, is to focus on some big picture algebra ideas that maybe weren't so clearly nailed down over the past few years. And trust me, at this point, it is a given that you understand some of these things. And so I don't want you to get lost in the first, 4 weeks of calculus, because then you're just playing catch up. Let me tell you, calculus is not a subject that you want to be playing catch up with, especially not for the entire year, especially not if you want to pass the AP exam, and especially not if you want to continue to take higher levels of calculus. So if you plan on continuing this journey, the algebra is not going to get any easier. The geometry is not going to get any easier. The limits are not going to get any easier. If you haven't seen limits, don't worry, you're in for one. So all that to say, welcome. I hope you're getting yourself prepared and you're going to take your calculus prep journey seriously, because if you do, how can you fail? I promise you cannot fail. All right. So let's get started. We're going to talk about a really basic concept of algebra here. The focus is average rate of change. It's a very simple concept. It's what we use to find the slope of a line between 2 points. I guess I should mention that. Let's make this a little bigger. We can find, or we can use this representation as the value of the slope of the line which connects any 2 points in space. Okay, and what exactly do I mean by that? Well, if you remember rise over run, that is a visual representation, but really what we're trying to understand this as is something which is changing. We're trying to figure out roughly how fast it is changing. Like an estimate. For example, if I drive from home, which I put 0, 0 as my location, here is my x-axis represented by time, and here is my y-axis represented by, I can just use s or x, something that indicates my position. If I drive 300 miles in 5 hours, that means that at the 5-hour mark, I should be at a location which is 300 away. That's not to say that my path of driving is just a straight line, but I can get an average of my movement by finding the slope between these 2 points. And so this little segment which connects these 2 points, it's a line segment. We can find how steep it is. We can calculate how steep it is. And when we do that, we're going to naturally have a measurement unit as a result, because this y-axis is representing distance in miles, whereas this x-axis, we use t in this case, is representing time, and the units there is hours. So if we do the simple rise over run formula here, we see that this rise or this change in my y value, which represents position, so a change of 300 miles in position over the course of 5 hours is going to give me a slope or a rate of change. So my average was 300 miles over 5 hours. Of course, this does reduce. So many students struggle with dividing by 5. It's like, dudes, just multiply by 2, right? You understand what I'm saying? So if I need to divide by 5, just multiply this by 2 and then move the decimal. Bam, 60 miles per hour. So my average speed was 60 miles per hour. Now here's an interesting idea to consider. All of that should have just been basic, right? That's really basic. But here's something to consider. Let's take it in the direction of calculus. Can I guarantee that I was going 60 miles per hour the whole time? Well, of course not. Just realistically speaking, if you've ever been in a car at all or a vehicle that, has to get up to speed, and there are stoplights and such and traffic sometimes, there's no way that I was going 60 miles per hour the whole time. My car didn't just immediately start going 60 miles per hour from my house the whole time through all the stoplights on the freeway where you can actually go faster than 60 miles per hour and then get to the hotel or whatever and just stop immediately like on a dime. That did not happen. I think we can all agree on that. But how about this question? And I'll type it. Can I guarantee that I traveled 60 miles per hour at some point during my trip, during my drive, let's say? That's an interesting question. Can I guarantee that at some point I was going exactly 60 miles per hour? Think about that one. I wonder what you think. Feel free to leave a comment, give a description of why you think that. In calculus, we're going to answer that question very specifically. So this is setting us up to understand rates of change through a very familiar concept, the average rate of change. Maybe it wasn't always called that. Maybe they called it average slope, or maybe they simply called it slope because it's the slope of this line that connects 2 points. But realistically, it's possible that I was, speeding up. I was going slowly at first, and then I was eventually speeding up. So maybe I went something more like that. Or maybe I was going really fast at first, and then I hit a bunch of traffic and I had to slow down. So then I wasn't going as steep. That's the idea. We don't really know what the path was. Maybe I passed the location and then came back to it. Who knows what my actual path was? I just know that a snapshot in time is when I started at home, and another snapshot in time is 5 hours later, I was 300 miles away. Okay? So that's the concept. Let's formalize it a little bit. Let's go back to our notion of rise over run. We also call it like the delta y over the delta x, which is pretty much the slope. How do we normally calculate it? Well, if you have 2 points, you have 2 x values and 2 y values. So you would do the difference in the y values, which is y2 minus y1, over the difference in the x values. These differences are telling us the change. So that delta, this triangle, it pretty much just means change. So how much did it change? And the way to notice how anything changes is you take the final amount and subtract the starting amount. That's how you identify change. If you have a positive result, then that means you had a positive change. If that value gives you a negative, that means you had a negative change. Like if I go from $3 to $5, what's the change? 5 minus 3 means I added 2. But if I go from like $8 to $1, then 1 minus 8, that's going to give me a negative, which indicates that I lost. The change was like a loss of whatever the number represents, right? So make sure we have the y2 minus y1 over x2 minus x1 clear. I know this all seems very basic right now. However, once it gets to calculus, you need to remember these very simple structures because you're going to have to be working with A's and B's and C's and X's and Y's, lots of different variables, things of that sort. And you don't want to risk missing points because you forgot the basic structure for the average slope formula, for example. Let's look at some examples. We're going to start with this quadratic function. And I have a couple of challenges at the end of each of these problems for you to do. We're going to take a look at the average rate of change. I should write that. Find the average rate of change of the function on the given interval. Okay. So here you're going to use the interval from 0 to 4/3. If you'd like, you can pause the video, give yourself a minute to work that out. See if you can calculate this. And when you're ready, come on back and you can see how we do it here. All right, so let's plug in our x values because this represents our x1, our x2. We need a y1 and a y2. We don't have 2 points yet. We have 2 individual x values, right? So we're going to have 0, and the y value is going to be f of 0. And then we're going to have 4/3, and the y value is going to be f of 4/3. So in order to get our y values, we need to plug the x values into the function. That should be no surprise. That's how we get y values. We plug in x values, or we plug inputs into a function and we get outputs. So here we have f of 0, pretty easy. It's just going to be 3 times 0 minus 2 squared, which is just 0 minus 2 squared, or negative 2 squared. It's a negative, but we are squaring it. So we have a point 0, 4. That's sort of like our x1, y1. Now when we plug in 4/3, this one is takes a little bit more work, but it's not too bad. I designed it fairly nicely, right? Because we're going to plug in 4/3, and 3 times 4/3 works out better than you might imagine. They're both compatible because we have a 3 and a divided by 3. So this is just 4 minus 2 squared, which is just 2 squared, which is also 4. Would you look at that? Okay, so what can we say? We can say that the y value for the second point is going to be 4 as well. And therefore, see what I did there? Because it's the 4s, all the 4s, therefore. Okay, anyways, therefore, the slope, the average rate of change, sometimes called A.R.o.C for like an acronym, just for short, the A.R.o.C, or the slope of the line segment between these 2 points, is going to be y2 minus y1. y2, that's our y1. And this is our x2, and this is our x1, over x2 minus x1. Well, the top is just 0, and the bottom is not 0. Anytime we have 0 on the top of a fraction and not on the bottom of the fraction, that just equals 0. If you need some work on fractions, I do have a video about fractions. It uses cookies. What a great way to learn about fractions. Alrighty, so the average slope in this case is 0. And what I encourage you to do, the challenge or sort of bonus exploration in each of these problems, is I encourage you to graph these. Whether you want to graph them by hand, if you can, that would be great. Or if you want to use a graphing software, use DESMOS, that's fine too. But what I want you to do is I want you to be able to see the line that connects those 2 points so that you can actually see the slope of 0. I want you to observe that there is a 0 slope connecting those 2 points. And then what I want you to do is I want you to answer the following question. Is there a point on the graph which has the exact same slope as the value of average rate of change, A.R.o.C. So in this case, you would be looking at the graph of 3x minus 2 quantities squared. And then you would try to look on the graph for these 2 points, 0, 4, and 4/3, 4. And then what I want you to do is I want you to determine if there's some point on the graph, from what you can tell, that has the exact same slope as the average rate of change. Okay? Is it clear what I'm asking? Let me just show you as an example. So let's say I have 2 points on some random function. I'm going to draw like a cubic function or something. And maybe my 2 points are here and here. And so the line which connects them, this one, it has a certain slope. We're finding that slope by doing the average rate of change formula. y2 minus y1 over x2 minus x1. Now my question is, are there any points on this graph which have that exact same steepness? See how the steepness is changing? Like this is very steep, but then it's starting to sort of flatten out a little bit. My question is, can you see approximately, I don't need you to find it, but can you guess whether or not there's a point on the graph which also has this exact same steepness as the line between these 2 points? That's what I'd like you to consider. There's no like right or wrong answer here. It's really just an exploration, but I would like you to do that because if you want to be prepared for calculus, you need to connect what you're doing numerically with what you're looking at visually. Okay? Let's do one more example here, and I'll again encourage you to take a look at the graph and see if you can maybe spot any interesting locations from that. So we're going to have a trigonometric equation, trigonometric function, which I'm sure you all are so excited to revisit. This is going to be a cosine function, negative 2 times cosine of 4x minus 3 pi on 2. And we're going to consider the interval from 3 pi on 8 to 7 pi on 8. There we are. Now, feel free to leave your answers in exact form. This is going to test your unit circle knowledge, but it's not going to go crazy, so you don't require a calculator. In fact, do not use a calculator on this one. Again, feel free to pause the video. Give yourself, 3 or 4 minutes to work it out for yourself. Then when you're ready, come back. See how we do it here. Alrighty. Got some air beneath the wings here by the beach. Let's establish that we have 2 points. We have x1 with 3 pi on 8. And so the y value is going to be f of 3 pi on 8. That's our first point. How do I know it's x1? Just because it's like first, like it's smaller value, comes first in the interval. So, pretty easy to determine that. But I think it's worth mentioning just because some people maybe flip it up. Maybe they mix it up a little bit. And so we have x2 is 7 pi on 8 and y2 is f of 7 pi on 8. Great. So let's find out what those values actually are. F of 3 pi on 8. I did design these problems to work out fairly nicely here. So we're going to have 4 times 3 pi on 8. This is all happening inside of the cosine, by the way. Minus 3 pi on 2. So this is going to give us negative 2 cosine of, let's be very careful in here. I got fractions. I'm subtracting stuff. I got pi's. Everything gets more complicated when pi is involved, just because of our deep love and appreciation for pi. All right, so 4 and 8 reduce. You need to be comfortable with reducing like that. Make your numbers smaller before you make them bigger. Why would you multiply 4 times 3 on top when you can reduce 4 over 8 first? Then you don't have to multiply anything on top. Then we just have 3 pi on 2. Oh, look at this. Minus 3 pi on 2. This is negative 2 cosine of 0. What's cosine of 0, everybody? You better say 1. You better say 1. It's not a threat, but you better say 1. Sorry if I made that sound like a threat. Okay, so we get -2 times 1. That's -2. And let's do the same for 7 pi on 8. So if we do 7 pi on 8 into the function, now we're going to have 4 times 7 pi on 8. Again, don't multiply the 4 times the 7. Why would you do that to yourself? Reduce the fraction. Make the number smaller before you make the number bigger. So 4 and 4, oops, let's use red. 4 and 4, factor of 4 and 4, that is, cancels. So we have 2 left on the bottom. And so this is -2 cosine of 7 pi on 2 minus 3 pi on 2. Oh, would you look at that? This is going to give us 4 pi on 2, or just 2 pi, yeah? And what is cosine of 2 pi? I better hear it again. Actually, I can't hear it again, because I have no idea what you sound like, and don't really care, but you should be screaming 1 again. -2, so very interesting when we have the same y values, is it not? 3 pi over 8 and -2. And then we also have the point 7 pi over 8 and, you guessed it, -2. So what I'd like you to do is find the average rate of change. No surprise that it's going to be 0 here. A.R.o.C is going to be -2 minus -2, and then 7 pi on 8 minus 3 pi on 8. The bottom doesn't really matter just as long as it's not 0, because we have 0 on top. This is going to be 4 pi on 8, by the way, which is just pi on 2. But 0 over anything non-zero is just going to give us 0. So that means the average slope between these 2 points, again, is 0. I have a feeling I designed this on purpose. Yeah, totally did. So again, I want you to graph the function. It'd be great if you can graph this by hand. I'm not kidding when I say graphing is a dying art. You should be able to graph this by hand. I don't care if it takes you, 4 or 5 minutes. You should be able to graph it by hand. So as a bonus, this actually is a challenge, is to graph this accurately by hand. Now, just as a bonus exploration, I want you to have the graph somehow, whether you do it by hand or use DESMOS, that's fine. And then I want you to identify these 2 points on that function. 3 pi over 8 comma -2, 7 pi over 8 comma -2, and then observe the line that would connect them. You don't have to draw the line that connects them if you don't want to, but look at what that line is like. Draw it on your own paper, on your own notebook, and then see if you can identify any points on the graph of cosine that have the same exact steepness at that point. And since cosine does something like wiggly, right, it like bounces back and forth, it definitely seems to have a 0 slope at some point. So determine if you can find any spots where it has the exact same slope. I guess it would be like, well, the -2 is going to be all the way at the bottom. So it'll be some 2 points at the bottom. And so the average line which connects them, there we go. So what I'm saying is, are there any points that seem to have that exact steepness? If we look at the steepness of the graph, like where it touches here, for example, it's pretty steep. Where it touches here, it's a little bit less steep. Where it touches here, it's definitely a little bit less steep. And then somewhere over here, it's like negative slope, right? It's like going downward, so the steepness is kind of like a negative. And then it's a little bit less negative steep. You get the idea. So are there any points on the graph that you can determine after you've graphed it which have the same slope value as this average rate of change that we just discovered? That is the question. All right, now the last 2 examples that I have you do are going to be requiring a calculator, because here we have the ln function. So here we have f of x equals 2. I like to put 2's in front of stuff. Doubling things, for some reason, it intimidates a lot of students, so I like to throw it on there. It's a very easy way to intimidate some students and, train them, get them stronger, get them comfortable with more intimidating problems. And we're going to look at this on the interval from, 46 over 9. Don't ask me why I picked these numbers. And 20 over 3. I don't remember what I was doing when I created this problem, but let's just trust and hope that I was thinking clearly. Now, calculator is allowed and encouraged. I still think it's a great bonus for you to be able to graph this by hand within reason. I think it's a great idea for you to be able to do that. I can't emphasize that enough, how good it would be for you to be able to graph all of these things by hand, like no problem. Seriously. Okay, so pause the video if you'd like to give yourself a moment to try this out. And then we'll just sort of plug and chug. I'm going to write my answers in the exact form, not using a calculator. But you can just finish it off if you'd like. So we have 46 over 9 as our x1. And so we're going to have f of 46 over 9. And the other point is going to be 20 over 3. And so we're going to have the y value as f of 20 over 3. A reminder here that plugging in x values gets you y values when it's a function f of x. If it were a function of y, like x equals f of y, you would plug in y values and then you can get x values. Or whatever type of function it is, you plug the inputs and you get some outputs. Okay, so let's see if this is as hideous as it seems like it's going to be. F of 46 over 9 is 2 ln of 1/3 times 46 over 9. Goodness, this is looking terrible. Minus 5/3. So let's just do our best here. This is going to be 2 ln 46 over 27 minus, we have to make this over 27 as well. Oh, good. This is going to be times 9 on the top and bottom of the fraction to give us 45 over 27. Well, that does seem kind of nice, at least. So we have 2 ln of 1 over 27. Which I guess isn't the worst thing, but it's also not the nicest value. Okay, now let's plug in 20 over 3. Let's make a little space there. Plugging in 20 over 3, we're going to end up with 2 ln of 1/3 of 20 over 3 minus 5/3. Who created this problem? Equals 2 ln of 20 over 9 minus, well, now I have to multiply by 3 on top and bottom for that fraction to get 15 over 9. This is going to give us 2 ln of 5 over 9. All right, so these are not the nicest values, but those are our y values. You can, again, plug it into a calculator if you want, like a decimal representation. 2 ln of 1/27th, which I really don't like writing it like that all too much, but it's fine. We'll be all right. And then we're going to have another point, 20 over 3, comma 2 times ln of 5/9. So let's go and find the average rate of change. This one does not look like it's going to be simply 0. The average rate of change is going to be y2, 2 ln of 5/9, minus y1, which is 2 ln of 1/27. And don't worry, I'm going to use a nice little trick in a moment. Over 20 over 3 minus 46 over 9, which can pretty easily be done. We just got to get the same denominator for these fractions, but it's not really that hard. Now, let's use the nice trick here. Remember that if we have logs like this, what we can do is, first we can take out the 2 because it's a GCF, but then we'll be left with ln 5/9 minus ln of 1 over 27, which means that we can write this as a fraction. ln of 5/9 divided by 1 over 27. Aha. And on the bottom, let's get the same denominator. This is going to be 60 over 9 minus 46 over 9. How did I do that? Just multiply 3 and 3. Okay, we're making some progress. So let's fix the fraction divided by a fraction business. 2 ln of 5/9 times 27 over 1 over 14/9. Great, we're making some good progress here. Don't multiply those numbers. Make the numbers smaller before you make them bigger. So we end up with 2 ln of 15, nice clean number, yeah, over 14/9. And then we can do the last bit of flipping the fraction we're dividing by, calling it 9/14. And once again, don't multiply the numbers if you can make them smaller first. So we end up with 9 ln of 15 over 7. That is the average slope. I have no earthly clue what that is. If I had to guess, I would say it's somewhere around 4, but I really don't know. Yeah, I would just guess it's somewhere around, like, actually probably even smaller, maybe like 3.6 or something like that. Now what I want you to do is I want you to graph this function. I can't stress this highly enough. It would be really great if you knew how to actually graph this by hand, roughly. But if you can't, or if you don't want to, or if you're not ready, work up towards it. And then soon you need to be able to graph this by hand. But just as an exploration, I want you to have the graph, whether it be DESMOS or your own work, and these 2 points represented on the graph, roughly. So if you want to use a calculator, that's fine to use a calculator and get some decimal values, but you need to be able to graph things and scale your graphs reasonably and start getting used to that. It's not a bad habit. And then I want you to tell me if you see any points on the graph which seem to have the same steepness as the slope of the line which connects the 2 points on the graph. Okay, and the last one I'm going to leave for you to do. You do not have to graph this one by hand. It is f of x equals 3 minus sine of quantity x squared. If you know how to graph that, I'd be pretty impressed. It's not something that you would have necessarily learned, but if you're diligent and if you use some good logic, I think you'll be able to figure out how exactly it works. Maybe. If not, it's totally okay. You can always feel free to just use DESMOS and graph it however you need it. All right. Oh, and let me give you the interval for that. It's going to be on the interval from -pi/2 to 5 pi on 4. So trying to do this by hand is not going to be easy. Why is that? Because these values are on the unit circle. Yes, the x values are, but once you plug them in, for example, -pi/2 squared is pi squared over 4. That's nowhere on the unit circle. So sine of pi squared over 4, probably not going to get that right. Same thing with 5 pi over 4. If I plug that in, 5 pi over 4, it's not just sine of 5 pi over 4. I have to square the 5 pi over 4, get 25 pi squared over 16, and it's like, where's that on the unit circle? What is sine of that? Who knows? The calculator knows. So you have to plug it into a calculator. Again, no problem if you have to use a calculator to evaluate, but the skills of graphing, that's something you're really going to want to be clear on. In fact, that's going to be our next topic of discussion. So I think this is a good place to wrap it up, leaving you with this problem. Go ahead and do the challenge exploration. The bonus exploration of graphing it and seeing if your average slope maybe is represented somewhere on the graph of the function. You play around with that on DESMOS if you'd like. And as a bonus sort of hard challenge on this one is to graph it by hand, to get a decent sketch of the graph by hand. All right. I think that's enough peppy blab out of me. I was a bit energized today, wasn't I? I think it's the sunshine and the beach vibes. Alrighty, so we'll see you next time.